Good morning. Welcome back. Any questions? Any comments? Now I want to go through a detailed example to show you how these some nice results we went through last time works in like a specific case. So this is example 2.2, and I also blended a little bit of assigned problems in this assignment. So this is pretty standard. Given a particle in an infinite square well with the following state. So we prepare the state. How we prepare does not concern us at the moment, but hypothetically suppose this is the initial state. This is some constant x a minus x if x is inside 0 to a and 0 otherwise. And the question is asking us to find psi in the subsequent times, and that means find what psi of x comma t. Good. Let me just sketch the function for you. Suppose this is my box. I think this is like a parabola, and the tip of the parabola is in the center, and this is something like that. So this is psi of x comma 0. This is x. This is x is equal to 0, and this is x is equal to a. Any suggestions? So what's the strategy? So the first thing we need to do always normalization. Good. And the second step, so I will spend quite a bit of time, but in detail, in very short. So any function can be written in terms of these exact separable solutions, right? Sines and cosines, which was actually sine only. And once you decompose this solution into sines, you can automatically put time dependence. So then let's start with our program. The first step is normalization. Normalize. So we want total probability to be 1, and we need to integrate from 0 to a dx a squared. Let me write it in 2 steps. Psi x comma 0 squared, and this is a squared from 0 to a dx. Did I write it? So this is x squared a minus x squared. So this a minus x squared is a squared minus 2ax plus x squared, and I multiply with x. So this is x squared a squared. So this is x cubed. This is x to the 4th. And this one is going to give me 1/3 a squared. X cubed is 0 at 0, or only write a cube minus 2a over 4 a to the 4th plus 1 over 5 a to the right? And this is a to the fifth, a to the fifth, a to the fifth. This is 1 over 3 minus 1 over 2 plus 1 over 5. And this is what? This is 30, 10, okay, 10 minus 15 plus 6 over 30, which is 1 over 30, right? Then A is going to be let me say, I think 1 over 30 times a to the 5. Then A is going to be 30 divided by a to the 5 root. Good. Let me check that. 30 or yes. So this is the normalization. And the second step in our program is decompose. Use expansion. So we said any function can be written in terms of sines and cosines. So psi of x comma 0 is also a good function. And this is going to be sum over n cn psi n of x. And cn's, the job is to calculate cn's. Cn from 0 to a dx psi n star of x uppercase psi x comma 0. Now let me write what this function is. So we have dx, we have this 2 over a sine n pi over ax. So this is lowercase psi of n star, which is real in our case. And this one is 30 over a to the 5 x a minus x. So this is the function. And I like to write this like ax minus x squared. And let me call this, there will be two terms, one from integration of this, another from integration of this. Let me call them 1 plus 2, not to keep track of the calculation. And first, start with 1. Combine these two, root 2 here, root 2 here, 2 root 15, a to the 6. If I take the root, this is a cube. And this is dx. This is sine n pi over ax. And I have a times x here. Yes. So why this expression? Why do we do this? Because the program was this. For an arbitrary function, I don't know how to put this function in a form that it satisfies the time-dependent Schrödinger equation. But if I decompose it, each separable solution, I know they are going to come with minus I over h bar E and t. So that's the only way I can put. So that's why in the program, the first step is to decompose, and in the second step, we are going to decorate time dependence. And this one is like we multiplied, so this side and this side we multiply with, if you want, the x psi star m of x, this one also psi star, and when you integrate psi star of m times psi of n, they were orthogonal, so that was Dirac delta, it just picked out the coefficient we need. It's always a good exercise. Even if you forget, just multiply both sides and integrate. That's the only trick.
X squared. It should be also square of the parameters.
So this one, this whole thing was the full given function. This is psi of x comma 0. And it was given to be, I think, x a minus x. Because I wanted to calculate each term separately, I put the x inside. This is ax, this is x squared. And in the normalization here, we had to take the square of the wave function. Right? That's why in the normalization, we had square of this whole thing. All right, any other questions? Now, this is the part, I don't think anybody if you enjoy this, good, but nobody likes a calculation like this, right? I don't enjoy it, but we have to do it. And how can we do this? And typically there's like one trick. You either know it or you don't know it. How do we take the integral of x sine x form of integral? By parts? Yes. So the trick is, by parts is like a very nice trick to learn. And I think you are going to see it has like very nice way of, it'll be very nice to understand many things in this course. So this is like du, this is v, right? If you want, let me also take this a out of our way. So this is a squared. And the trick is, so this should be u times v minus u dv, right? And here u is going to be integral of sine. So of course I also need to put boundary conditions. So like integral of sine is going to be u, then this is going to be minus cosine n pi over a x divided by n pi over a. So this is u, v is x, and boundary conditions are 0 to a, and minus integral, there is one minus from this, another minus from the u term. They are going to combine to be plus, and this is exactly the same thing. And dv is going to be dx from 0 to a. Is that good? And it's okay to make mistakes, but that's the trick. No cell phones in the class, and no cell phones anywhere accessible. Okay. Thank you. Now this one is minus cosine n pi, right? The first one, I put a, and if I put 0, it's going to be 0 because of x, divided by n pi over a, plus the second one, this one is also, let's integrate a over n pi cosine, and the integral is going to be sine n pi over a x divided by n pi over a, and the boundaries from 0 to a. And this one is going to combine. This is a squared, n squared, n squared. Let's erase this. But sine n pi is 0, sine 0 is 0. So this entire term is not going to contribute, which is nice. Then this whole thing becomes minus a over n pi cosine n pi. So this is, now we are done. Let's go back. We forget what we were doing, but what we were doing was we got term number 1. Now we need to do the same thing with term number 2, because for x we had to do 1 by parts, for x squared we had to do 2 by parts. How many people want me to do this, or how many people want me to write the result? How many people want the result? Okay, nobody wants me to do it, so let me write the result. So to calculate as an exercise, since nobody wanted, let me just go back to results. Then 1 plus 2 gave, after cancellations, 4. Can I explain? Oh, yes, I can write 2 so that you can compare, right? Yes, that's a good idea. So what I found for 2 was minus 2 root 15 divided by a cube, found minus a cube over n pi cosine n pi, and plus 2a cube over n cube pi cube cosine n pi minus 2a cube over n cube pi cube. Good. And the final result is Cn is equal to 4 root. So what, some terms from here in 2 is going to cancel some terms in 1, and what remains is very nice. It's like n cube pi cube 1 minus cosine n pi, and this is equal to 0 if n is even, because if n is even, cosine is 1, 1 minus 1 is 0, and otherwise it's minus 1, and it's going to be 8 root 15 divided by n cube pi cube if n is odd. Good. So I think if you make mistakes, it's okay. I mean, there is no way there is a calculation without a mistake, and there's never a paper or a book without a mistake, and there's never a code without a bug, right? It's part of the job, but we can always try to check. And Mathematica is a great way to do this. And let me just expose you very briefly how to do this, because these things can be done very nicely there. So all you need to do is integrate, right? And I will take out these coefficients, and then I'll write the rest. So this is sine. Can you read? Should I increase? Also, if you cannot see, please let me know. I can make it a little bigger. Magnification. Better? So this is sine n pi over ax times ax minus x squared. Ax minus x squared. And I want to integrate this thing from x0 to a. And that's the result, right? Sine is 0. This is exactly what we found. 2 minus cosine. Right, at this moment, because you are trying to develop skills, I think you need to do this by hand. But when you get experience, I don't think anybody sits down and calculates these integrals. Yes? Here? Yes. 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 Do you want me to do this? Let's do this. It's like real quick. So what we expect is like any function psi, you can also use it for f, psi x comma 0 should be written as an expansion in terms of some coefficient Cn and psi n of x. And what we say is like let's multiply both sides with Cm star of x and this one psi m star of x. And now we integrate. So this is dx and this is also dx. And now this is our celebrated Kronecker delta, delta nm. And delta nm says that in the sum for n, pick m and leave everything else. So this is Cm. Then our expression is Cm dx psi m star of x psi uppercase psi x comma 0. But m is a dummy label. I can put anything I want. I put back n. Good. It's the same trick. If you learn it once, you get it. Okay. Then now we know how to write the time dependent. Any other questions? Let's write the full time dependence. X comma t is going to be, so it was Cn, but we found Cn. Cn is this for odd ends. So let's write this thing. So bring this down. So this is Cn. This is n is equal to 1, 3, 5, dot, dot, dot. So this is Cn. There's 2 over a sine n pi over a. This is the psi n, and there's e to the minus I over h bar. And this is now I'm writing the energy, h bar squared over 2m pi squared over a squared n squared times t. And this is the desired result. So as an exercise, okay, another exercise for you. I think the best way to understand a function is plot it and look at the pictures, right? Humans are like visual creatures. We don't work with equations. We work with visual simulations. Plot in different times and see how it evolves. Right? You can, in Mathematica, you can plot anything with plot function and check out what to write here. Any questions? Now let's check another thing we have previously demonstrated more in more abstract terms. Let's see if normalization is preserved in time. So this is from 0 to a dx psi. Now I'm writing the full psi with all of its time dependencies. Now inside each psi there is a sum, and there is like two sums multiplied. At the end there will be a sum for psi star, another sum for psi, and there will be some integral dx, right? So this is Cm star Cn. So there will be psi m star x, psi nx, and there will be e to the I over h bar, e m minus e n times t. So I didn't do anything, I just substituted. And I combined exponentials and I combined sums and integrals. Any questions here? Now this integral is from 0 to a. It only knows about x-dependent things. We can immediately see the x-dependent things are here going to give us our celebrated Dirac delta. Good. And this Dirac delta is going to kill one of the sums at the end. And when m is equal to n, em is equal to en. So this term is going to also go. At the end, what we have is n Cn squared. Good. Any questions? And we have Cn's. Let's calculate. So Cn's were n is equal to 1, 3, 5, dot, dot, dot. And it's here.
You explain the current about the conjugate function.
So this part, so I wrote the full expression. Now I see that this integral is going to go and find anything x dependent. All these things are constant, so you can just push them through the integral. So then separate out dx psi m star psi n, because I know these are x dependent. Sometimes that's why I don't write it. And now I know this is delta m n. And when I see this, I'm happy because I can not only just get to the integral, but also one of the subs. Good.
It's gonna be a times Cn squared.
No, this is Cn squared, right? Like our expansion is like what? Our expansion says psi is written in terms of this, right? And this a, you are talking about normalization, right? Normalization is taken into account here. All of these factors are taken into account. And that's why I want to check this. Let's check if I missed anything, because if I did, so this is not going to be 1. Right? I also need to take square because this is Cn, and square of Cn is, so this is 64, this is 15, this is n to the 6, this is pi to the 6. And you can see this is 64 times 15 divided by pi to the 6, and 1, 3, 5, 1 over n to the 6. And things like this, in the past, we had to go look at integral tables. We had like volumes of books that we would just spend sometimes hours to find what we want. But today you don't need to do that, right? You can even copy and paste it in ChatGPT or like screenshot, or you can write it Mathematica. Typically, if you ask this, we have to give this to you in the exam, so nothing to worry about. But now, as a researcher, this is how you calculate these things. So these are odd. So the way I write odd is n to n plus 1 to the 6th power. And I need to sum n 1 to infinity. So this is power. Six. Oh, I think I need to start from 0 because the first term is 1. And to make this, I need to sum from 0. And this is pi to the 6 version. So this is pi to the 6 divided by 960. And this 960 turns out to be this. Check it out. This pi to the 6 is this pi to the 6. And this is 1. So there is no a here. So a is, because I know this is 1, I know I have taken care of everything.
The integral, inside of the integral should be Cn squared, right?
So here is this.
About, yeah.
Here, this sum,
Its integral is x times n squared,
uh-huh,
and x goes from 0 to a.
uh-huh.
Where did the x go?
So do you want to write this? Let's write this thing carefully and see how did I write it. So this is what I want to write. So right now you don't have any objection to that, right? So this thing is from 0 to a dx. So let me use m for this. Cm psi m of x e to the minus I over h bar em t, an entire thing complex conjugate times exactly the same thing, but with not to mix up the indices, I have to use another index here. So this is n, this is n, so this is n. Is that okay? Oh, this is also n. Yes, absolutely. Now I take m, n, right, outside, m, n. I have integral from 0 to a dx. I have Cm star, Cn, psi m star of x, psi n of x. So this, because of conjugation, becomes I over h bar plus em minus en t. And now I look at this. So the integral only knows about this. So let's copy and see what I mean by you can push it. So you can push all of these factors to innermost operation like this. Okay, let me not copy. Let me just take this and take this, because this thing is going to walk through all of these guys because it doesn't know about this. Then I combine this here. I combine it here. And at the end, I have the Dirac delta by itself. And the rest, right, this is delta mn. Once I have delta mn, I not only get rid of this, one of the sums, I also get rid of exponents. And this is m or n, whichever is your favorite, Cn squared. And when we calculate that, we found 1. So let's do one more thing, because this is the key, right? This is the power of separable solutions. So we actually had a non-separable solution. The solution given to us was non-separable, and we decomposed it in terms of separable solutions. Then I know how to put the time evolution. And that's the only way to put time evolution. So the question is, if a measurement is made on this NIP psi, what is the probability to get E1? And this one, like, you should immediately answer that, because this is not a calculation question. So what is the answer to that? What is the probability to get nth state from this psi given to us? Or the coefficient of PC1, right? The coefficient is, right, these Tn's are probabilities that are adding up to 1, and each is the probability to have the corresponding energy states. Then E1 is going to have P1, which is going to be C1 squared, and C1 is here. This thing. And this is, you can put it mathematically, I found something like 0.99927. So a big portion of the state is actually ground state. Any questions? Mm-hmm. Can you say it one more? Yes, yes. So now key is like if like there is like one electron, right? And if you do one measurement, now the state is going to collapse to this ground state. And from now on, if you do the same measurement, you are going to get E1 100%. Suppose you made first measurement and it collapsed to, I don't know, 10th state. It is extremely unlikely. But if the first measurement is non-zero, right, there's like a non-zero probability, and extremely unlikely things are still likely. Suppose it happened, in the second measurement, you are going to get extremely unlikely result 100%, because it collapsed to that state. That's the key concept. Another thing we postulated before, or like we like explained, what is we introduced so-called expectation values. What is the expectation value of energy? So there are, okay, since we have time, let me tell you how to calculate it in two ways. And then finish after that. So method number one, this is just, by the way, all of these things just to expose you to language and jargon and build up vocabulary so that we can do these things more systematically at the end in the next chapter. So we said, let me sketch this out and we can do this details like exercise. So easiest way for us to do this is we have this. How did I do this? You can do this psi star x comma t and h and psi x comma t. Now the first thing we need to say about this in the first method is because energy is time independent, I anticipate this thing to be the same in all times. So I can just put this 0. And a second step, so this function is given to us. It is like this a x, a minus x, but h is also given, right? Minus h bar squared over 2m d squared dx. And I can hit this side with these derivatives, and what remains I can integrate. So do it as an exercise. I can also do it if you want, but let me then try not to bore you early in the morning exercise. And what I found here is it's in the notes, 5 times bar squared over 2m. But the warning about first method is sometimes we may not be given a nice function, right? Maybe you are in a lab and you are preparing the state. You may not be able to prepare the perfect state you want. Sometimes you may have to deal with a state which doesn't have a derivative, right? For example, also part of exercise, consider an initial state like this, which is a problem in your book. Because the derivative is not well defined, you will not be able to calculate this integral. Later, we will also go through how to deal with these pathologies. But for the moment, just know that you can bump into, walls, and that's okay. But for things like this, method 2 will always work. What is the method 2? Method 2. Expectation value of Hamiltonian is again dx psi star of x comma t h psi x comma t. And I think last time what we did was we operated and we did all the integrals, and what we found at the end was n Cn squared En. We found this because this was the nice thing about separable solutions. And if you do this, you again have like a series. This is n. So this is, let me write the result. This is again n is equal to, so exercise, because nobody wanted me to do it here, I'm writing the result again. Ask me if you want. So this is 1, 3, 5, 64, 15 divided by n to the 6, pi to the 6, h bar squared over 2m. Now I'm writing the energy, pi squared over a squared, n squared. Now you have a series that you need the sum, n squared times n to the 6, 1 over n to the 4th, and odd numbers. And you can also put it in Mathematica, and Mathematica also gives you the result in no time. And here in my notes I found h bar squared over m a squared, which is same as method 1. But the nice thing about method 2 is, even if you have some function like this, which is not nice, method 2 will always work. All these discontinuities and things are taken care in method 2.
The first method there wasn't
Then that's wrong. I think there must be a squared here. Yes, good job. H bar squared over m a squared. So that's the, I think there's also note 2 here. Let me check my notes. H bar squared over m a squared. In my notes I have a, but it should be a squared. So this is the unit of energy. And this one is also m a squared. Yes. So this is also that. Then here is the upshot. Like, let's simplify all of these things, series and things. If you are given a state, psi of x comma 0, some a, psi 1 of x plus psi 2 of x, right? Now the components, this is nice because the components are already given to us. So from normalization, immediately we can conclude this is a is 1 over 2, because I know this is orthogonal, and if you take the square, 1 plus 1 is 2, and I have to take 1 over 2 other side to get that. And probability to have E1 is 1/2. Of course, if you get E1 at first measurement, the subsequent measurements are going to give E1 100%. And similarly, probability to have E2 is 1/2. And expectation value of energy, or Hamiltonian, is sum over n, probability 1/2, E1. Okay, let me just write it. There is no sum here. Right, this is Pi, Ei. This is 1/2 E1 plus 1/2 E2. And you can, as an exercise, consider, we did this a little bit last time, but you can also do it again. Time-dependent probability, expectation values, and variance, and things like this. Okay, any questions? Yes?
While making a measurement, we sometimes find an exact state. While we're preparing to this simple square, we probably give it some energy. And sometimes our energy that we find is exceeding our prepared energy.
It's not exceeding. Our prepared energy has all energies inside, right? It is not exact energy state. So what we have here is we prepared some non-separable solution. But in this solution, there's all excited state up to infinite. Yeah, exactly. Sometimes very high likely result is very low energy because that's the preparation.
This energy
It didn't go anywhere. It's always there, right? Yes. Uh-huh. Mm-hmm.
and I must find most of my measurements,
Mhm.
let's say 2,
Mm-hmm.
and very unlikely I find 100.
Yeah, like first, expectation value is not the value, right? Like, for example, the average value of energy in this room, or H, let's say, average H could be 23.5. It doesn't mean you are going to go and find someone with 23.3 years old, right? There are some below, some higher. Just because you didn't find it doesn't mean it doesn't exist, right? So the energy expectation value is not energy itself. And the state you prepared is like a complicated state. It's not an exact energy. If you want, there is also a variance in energy. So when you measure, also measurement is a non-linear process. Measurement itself does not necessarily conserve energy, right? You take the wave function, you collapse it. It's a non-linear, non-energy conserving process. That's the thing people get most annoyed about Schrödinger equation, right? You use linear, 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 and then when it comes to measuring things, you say, oh, it's non-linear. It's also a sudden, discontinuous jump from whatever it was to like what you measured. And how do you explain it? I have no idea. Yes, that's what it is. Yes. All right. Let's give a break.